I'm Joe Munchak. I'm a principal atmospheric data scientist at Tomorrow.io, and I'm going to share some of the exciting data that has been collected by our new microwave sounders that has been proven to really highlight a lot of different weather features, but I think one of the most impactful has been the recent tropical cyclone activity. So just to give a quick background, microwave sounders are very useful for a wide variety of things. They're kind of the Swiss Army knife of weather satellites. They can measure temperature, they can measure humidity, they can measure precipitation. They see through clouds, but they can also see patterns of weather that are associated with clouds. So they are a great complement to the geostationary satellites that we have that provide visible and infrared imagery. Microwaves are looking a lot deeper into the clouds and seeing things underneath that you can't see in those images. And that's why they're particularly useful for hurricanes and typhoons. So I'm going to walk through a few highlights of some data that was collected by Tomorrow S1 and Tomorrow S2, which were our first two microwave sounders that launched in August. We started collecting data less than 2 weeks after they were launched, and given that it was the height of hurricane and typhoon season around the world in the northern hemisphere, there were a lot of cases early on where we saw the potential of this data. So one of the first cases we saw was Super Typhoon Yagi. This was a very powerful typhoon, the equivalent of a Category 5 hurricane that struck southern China in early September. And these are some of the scans that we happen to get from Tomorrow S2. So what you're seeing on the top are two window channels. So those are the frequencies that penetrate closest to the ground. So we're seeing surface temperature. We are also seeing the clouds and precipitation in the areas of the storm, like the eye wall and the rain bands. And on the bottom are some composites that we've made of some of these channels, as well as some others. So on the left is what I'm calling a window channel composite, which is the two channels above plus another one that's more sensitive to temperature near the surface. And this gives us a picture where there's clear skies. Actually, over the ocean, it looks like a very deep blue color. And actually, how deep that blue color is depends on how much water vapor there is, or if there are low-level liquid clouds. So it's intuitively appealing in that way, that the oceans look blue, land can look brown or dark depending on its temperature. And then once you have clouds in the air, what they do, especially if they contain a lot of ice aloft, which is associated with precipitation, they reduce the amount of radiation reaching our microwave sounder, and that shows up as a colder temperature, which you can see here very well associates with the cloud patterns on the lower left. On the lower right, we have what's called a water vapor composite. So this is looking at water vapor at different levels of the atmosphere, converted to red, green, and blue bands. And typically what the pattern you see is that as you go higher in the atmosphere, the temperatures get colder and there's less water vapor. And when the atmosphere is following that typical pattern, what you see is like, again, more of a bluish color, because the blue channel is associated with colder temperatures, which are translated to stronger blue colors in this composite. What happens when there's clouds and precipitation is that all of the channels get much colder, and they do so equally, so they show up as white. And so it very clearly lets us distinguish where those precipitation producing clouds are. And sometimes you see reddish colors, which means that the clouds are either very low levels, or maybe we're seeing snow on the ground. So there's a lot of utility in these composites that really highlight the depth of information we're getting. And even these two are only using 6 out of the 12 channels that we measure. So there's a lot of data about atmospheric temperature that's not being shown here. But one thing that we can do is take a closer look at temperatures with these microwave sounders as well. And what I'm showing here are, again, some of those channels that I didn't show before that are showing those mid and upper level temperatures. And usually these channels look very uniform. You see this, the only pattern that you see is that typical, maybe what you see in channel 6 or 7, where it's warmer at the center of the scan and colder on the edges. And that's just an atmospheric effect where you have a longer path length through the atmosphere, and you're seeing at higher levels on the edge of the scan than at the center. And that's well known and well accounted for. It's something that we can correct for very easily. But what's interesting is when you see departures from that typical pattern again. So we do see the cloud and precipitation influence, especially in channels 5 and 6. Channel 7 and 8 are actually so high in the atmosphere that you're seeing above the clouds, above where the storm is really intense, and into the lower stratosphere. And there what you see in a hurricane is this phenomenon called the warm core. And what's happening is that all of the heat that's coming from the ocean that's going into the thunderstorms around the center, around the eye wall that are strengthening the storm. The hurricane is basically an engine that converts the energy from the ocean heat into heat in the atmosphere right around the eye. And so you see a very distinct, what's called a warm core anomaly right at the storm center. And it's actually been shown that the strength of that warm core anomaly is very closely correlated to the storm's intensity. So the fact that we see it so prominently in this storm is because it was such a strong typhoon, again, the equivalent of a Category 5 hurricane. And we can see that warm core anomaly very distinctly in the data. And this is something that is is where our particular microwave sounder really excels because of how its channels were defined and how good its resolution is and how low the noise is in these channels. A lot of new technology went into these particular channels that's never been flown in space before, and we're seeing better quality in this data than we are from any other satellite that measures at these frequencies. Here's another snapshot about a day later, right as Super Typhoon Yagi was going to make landfall. So once again, we captured that storm structure very well in these images. If you put all the scans together, again, we get about 2 per day with the first 2 satellites that we have based on where their orbits are. Of course, that will be increasing quite a bit as we continue to launch more satellites throughout the next 12 months. Closer to home, we had Hurricane Helene, which of course caused devastating flooding in the southern United States in late September. And this series of slides are just going to show how Tomorrow S1 and Tomorrow S2 captured its development from a tropical depression to a tropical storm and a hurricane. And you can see the increasing organization. You can see an eye wall start to form as those storms wrap around the center, as evidenced in these images. And then just 12 hours later, the organization continues with, you can see a lot of the fine detail of the rain bands here. Again, if you were looking at a geostationary image at this time, it would just show a solid cloud deck without all this underlying structure. Really highlights the value of the microwave data that we're collecting from the sounders. And again, we captured an overpass just after landfall in the Florida Panhandle here. And you can see the extension of all that moisture into Georgia and South Carolina and North Carolina, where it caused that devastating flooding. Again, we can look at the temperature anomalies, and Hurricane Helene was not, even though it was a strong hurricane, it was not nearly as strong as Super Typhoon Yagi, so the strength of the warm core anomalies is not as strong, but we still do see it. Again, a key signature of a strong storm in the data. There was another hurricane that you may not have heard about because it mainly stayed out of sea and didn't cause much harm to anyone on land. But we happened to get a lot of really good data collected from this one. This is Hurricane Kirk. And at this phase in our satellite's operation, you remember that we have 2 satellites that were launched, Tomorrow S1 and Tomorrow S2. And what we're doing is we're doing this operation called phasing, where we actually allow the satellites to drift apart so they can improve the global coverage. So rather than having 2 satellites that are observing the same location at the same time, we want to get them on opposite sides of the Earth so that they're observing the same location about 45 minutes apart. That's about half an orbit. And at this point in the staging, they were about 8 minutes apart. And so you can already see, if you take the data from one and animate it with the other one, you can see the storm's rotations start to pop out in just that 8-minute time difference. So this was really exciting to me to see, because it's showing that we're doing a really good job referencing the satellites to the right location geographically, and in such a way that we can pinpoint this rotation. And again, it shows a lot of evolution of the fine scale structure during this time interval as well. If you put all of the Hurricane Kirk overpasses together, this is just a little composite I made. You can see, again, we're getting those snapshots each day at each point in the storm's life cycle. You can see it grow from disorganized thunderstorms to developing an eye wall, and then showing this multi-banded structure as it grows in size late in its life cycle. So those are the highlights that we've had. Hurricane Milton was, of course, another strong storm that just affected Florida. We captured a few scans of it, but it wasn't as ideally positioned as some of these other storms were with our scans. Again, one of the benefits by next hurricane season is that we'll have many more satellites, so we're not going to miss any storms with all of the satellites that will have in place by this time next year. I mentioned that we have the main satellite data source that most people are aware of are the geostationary satellites that collect visible and infrared imagery. And this is very valuable. It's updated every 5 or 10 minutes, depending on where you are in the world, and it's very high resolution. But it's only seeing the tops of the clouds, and that can only tell you so much about a storm. So again, we have that information, and we can use it, but we also have this new information that's penetrating into the clouds and seeing the structure underneath, which for hurricanes can sometimes be very different than what you see at the top of the cloud. So they really complement each other. Now, we're not the only passive microwave instrument out there. There are about 10 or so similar sensors operated by government agencies worldwide. One of the main differences between our sensors and theirs is that we are utilizing commercial ground stations to get much lower latency. So you might need to wait an hour or 2 hours to get data from one of these government satellites after it passes over a storm. With our network of commercial ground stations, we're getting an average of 40 minutes, and in some cases as low as 20 minutes after the storm. Another difference is that with a full constellation in place, again, by this time next year, we're going to be getting these scans every hour or better rather than about every 3 or 4 hours, which is the current standard from the government constellations.